Here's some more notes on section 6.5, and this is exploration 2 on page 365. So open your books, make sure you're looking at this exploration. We're going to go through these questions, and they're pretty good. I've kind of worked them out, but it's a good thing to check out. Okay, it says, and again, this is for positive population P, and this is our logistic differential equation. The rate of change dP, the rate of change of the population with respect to time, is a constant times the population, and then this is our carrying capacity. So this is our limiting factor, m minus p, and where k and m are positive constants. This is what I should have said in the last notes. I thought I said it someplace, but k is positive if it's growth, and m is positive. That's our carrying capacity. We're not going to have a negative carrying capacity. All right. So take a look at this, and I put my answers down, so I better cover them up here. Number 1, for what values of p will the growth rate dp to dp, the growth rate dp dt be close to 0? Well, if we look at the graph, that kind of helps. And the growth rate is actually the slope of this curve. And if we don't think about the very beginning, when is it going to be close to 0? When will this rate be close to 0? It's when the slope will be close to 0. So here the slope is increasing. It's at its largest, and now it's decreasing till I get over here. So it's close to 0 when the population, this is the population, and this happens to be the value m, but this is the population. I guess I should write over here. P as a function of time, and this is time. So you can see as the population approaches m, then the slope here, or the rate of change, or the growth rate, approaches 0. All right? So the answer is when p is close to m. When my population gets close to the limiting factor, of course, and that m minus p is going to be close to 0. So if that makes sense, you think about that. Remember that limiting factor. Okay, and number 2, as a function of p, y equals k, p m minus p has a graph that is an upside down parabola. What's the value of p at the vertex of this parabola? Now, I just have to think about this. So this was the function they gave us, and they said this is an upside down parabola. Now this is my growth rate as a function of p. They just called it y, but it's actually dp dt. Same thing. And you can see up here. And then if we multiply this out, we have kpm minus kp squared. So you see this is like, well, I rewrote it like this. And I put the negative kp squared in front, and plus km, and I put the p next to it, and plus c. So it's like a quadratic in terms of p instead of x. And you can see that this is a negative, so it's going to be shaped like an N, so it's going to be concave down. And if we want to find out the value of p, which is kind of like the x in our quadratic equation, we want to find out where that's going to be at the vertex. We just use our good old formula. It's usually x equals minus b all over 2a, but in this case it's in terms of p, so it's p equals negative b all over 2a. So there's my negative, there's my 2 from the formula, and my b was km. See that? And my a was negative k, so I just put this in the formula. K over k is 1, negative over negative is positive, so I have 1/2 m. Right? Well, this is the rate of change, so the rate of change is actually at a maximum at 1/2 m. So if we look over here at this graph we were talking about, remember the rate of change is the slope. It's the slope of our population curve. This is the population curve, but the dp dt is the slope. Then it's going to be at its maximum right here, and that just happens to be 1/2 m. So I can write that in now. I didn't want to write it in at the beginning, so that would be 1/2 m. Okay, so that's at 1/2 m. That's when, and then you can see that you could probably guess that that's about where it's the steepest. So that's when the rate of change of the population is the greatest at half the carrying capacity. Now I just kind of drew kind of a sketch of this function. This is y of p, which is actually dp dt as a function. And you can see that at half m, that's the vertex, and it goes down. So the rate of change is increasing, increasing. Now it's decreasing, 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 just like the slope of my original graph. If you, again, you look at the slope of the original graph, the slope is increasing, 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 increasing until I get here, then it's decreasing, 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 decreasing here. Okay? So the graph of the growth rate begins a downward trend at p equals 1/2 m, causing a decline in the growth rate. This is a little bit formal way of saying it, but basically if we graph this parabola here, we can see that the x value of the x value of the vertex, or the horizontal value of the vertex, is at p equals 1/2 m. And when we get up here, our growth rate is increasing, and then it's decreasing. This is actually the graph of the growth rate. Okay. Number 4, if the initial population is less than m, if the initial population is less than m, is the initial growth rate positive or negative? Well, the growth rate is just the growth rate. So let's just take a look at this. So this is what I did. So if the initial population is less than m, that's the same thing if I subtracted p from both sides. I'd have m minus p is greater than 0, which is positive. So this is my growth rate, dp dt, and k is positive. We just told you that. M is positive. I'm sorry. Well, m is positive, but k is positive, p is positive, and m minus p is positive. So I got 3 factors here. They're all positive, so my growth rate will be positive. If the initial population is greater than m, is the initial growth rate positive or negative? So the initial the initial population is greater than m. So here the initial population is less than m. Here the initial population is greater than m. Well, if I just subtracted m from both sides, or if I subtracted p from both sides, I got m minus p, and the arrow's pointing towards that, so m minus p is less than 0. That means it's negative. Well, again, we have dp dt, and that's k, which is positive, times p, which is positive. But in this case, m minus p is negative. We'll have positive times a negative is a negative. So there my growth rate would be negative. And then number 6, and think about these questions. Go back and work through these again, because this is pretty good. If the initial population equals m, what is the initial growth rate? Now this is a real tricky one. You might think that it's 0. Well, the growth rate is at a maximum because it can only decrease. All right? In other words, if your initial population, and this, like I said, this is hard, you got to think about this a lot. If the initial population is at m, the carrying capacity, you can't add any more people. So what can you do? If you take a planet, if you take an island that's only capable of supporting a little island, 500 people, and you put 500 people on there, it's not going to get bigger than 500 people because, there's not enough food for them. So it can only go down. It might be able to sustain that, but it's not going to go up, that's for sure. So the growth rate is at a maximum because it can only decrease. And if you see the graph, if I'm up here I can't go any farther. All I can do is go down, because this is the maximum. So that was a tricky one. The growth rate is at a maximum because it can only decrease. And the last one, number 7, what is the limit as t approaches infinity of the population? And does it depend on the initial population? Well, if you take a look at this, we do have a horizontal asymptote, which is m. So as t approaches infinity, this is approaching what? M. So I can say that the limit as t approaches infinity of the population equals m. And there's nothing else in there. It doesn't depend on p. It's just always going to approach m, so it depends only on m. All right? So take a look at this. Try to think about it. It's kind of tricky. Some of the things are kind of tricky, but it does give you some insight into how these logistic curves work. So that's exploration number 2. Very important.